All right, welcome back. It is Friday. It's pretty early. Statics and a little more friction. So remember that quiz came available today. Get that done, submit it. And you have a homework set. And there's no face-to-face. So.
You understand you gotta get more eyes. Am I your lover or I'm just your vibe?
All right. Let's talk about the static angle of friction. I keep looking at the microphone, so that's kind of not great, but it's all right. I'm going to rotate you around and we're going to work a problem a different way. So you can always work a problem or attempt to work a problem by summing forces in the X and the Y. That works on most of the simpler problems. The other day we worked one that had to be two equations, two unknowns. The other way to work that problem would be the way I'm going to show you now with the resultant friction force. So it's just another method that can be used. So it's super handy in wedges. We might not do a lot of wedges, but that's where it really comes into play. But you can use it on any problem, and I'm going to use it on a simple one that we've worked in the past. All right, so if you have a block that is on a surface, I'm getting my calculator, sorry. Guess I wasn't 100% prepared. On a surface, I put it on a pretty rough surface with a 0.5. So this could be like a box on carpet, pretty hard to push, 500-pound box. But the question is, and you can do this, you can answer any question going this route. But let's say the question is, how much P do we need to move the box, right? So that's going to be impending motion. That's going to be the very top of the friction graph curve. So the very top of this thing, right? If we want to know, like, how much would it take to move something, you want to calculate F max. The equation relationship we're going to use is this one. And it says the tangent of the static angle of friction is equal to F over N, which is also equal to mu S. So that's the relationship between the resultant friction force and the system. So this is the resultant friction force. It is the resultant of these two components, F and N. So, you know, trigonometry, F is here. You can see why we use tangent. Tangent is F over N. This is the static angle of friction. This gets drawn in the maximum friction force condition. So you can't come up with calculated friction from this. You can come up with maximum situation, maximum. All right, so this static angle is important. It's also called the angle of repose, which we talked about the other day. But this is the relationship. Tangent of that angle is F over N or US. So tangent of the static angle is F over N. And from this relationship, we know that F over N is equal to mu S. And we can use this, right? Because we can put in our friction would oppose motion. So here's my F max. N always goes in normal, right? And here's the deal. R is always between F and N. So when F flips over here, R is over here, right? So this resultant friction force is always between these two, and the static angle is always here between N and R. So that is the important piece. When you put R in, N and F disappear, and you're just left with 1, 2, 3 forces. So when you use N and F, you have 1, 2, 3, 4 forces. You can't do a forced triangle. But if you pull these two out and just put R in, then we have 3 forces, and we know that 3 forces will create equilibrium in a closed triangle. So let's calculate. If you're given the coefficient, you can calculate the angle. Right? We can say, oh, the static angle is equal to the inverse tangent of the coefficient. And if you're given the coefficient, which you most of the time are, you can come up with the angle. So 0.5 inverse tangent. 26,565 degrees. That's this, right? So one of the strategies for solving friction problems is to put the resultant in and take away F and M. Get rid of FM, get rid of N. When you do that, it creates a maximum condition because you're using the maximum friction force. You're using the coefficient, okay? Just keep that in mind. You can't necessarily, well, you can determine sliding or not sliding, but you have to kind of think deeper. This will solve for P at the maximum condition, right? So then you can go straight, because now you see 1, 2, 3 forces, because these two are gone. You can go straight to forced triangle. And I always draw a forced triangle, you know, with the vertical and then the horizontal, if there is. I mean, P could be off at an angle, that would complicate this, right? But tip to tail, and then R closes it. Now, we don't really care about R, right? We don't need to know that value. What we want is P. And P is this bottom force. Now, we do need to get our angle in because one side is not enough to solve this triangle. And if this is a right triangle, but if it was a non-right, then you might even need more information, right? So you might have to dig out more angles. Like if P was up at 20 degrees, then P goes in at an angle, and now you have a non-right triangle. So most often these friction problems that you use, when you use the resultant friction force, you end up with non-right triangles, but this is a pretty simple one. Okay, so where's this angle? This angle is between vertical and R, between vertical, not necessarily N, but vertical and R. So here's vertical and R, that's the 26.565. Okay, so and P is what I want to know, so I'm going to use the tangent of 26.565. Tangent of this is opposite over adjacent. So P equals tangent and then 500. 250 pounds. All right. So let's check it. So that's the result. That's our new method, right? Let's do it by the old method. So the old method would say, okay, don't put R in. We're going to use F and 500 and P, right? And since P is horizontal, I can just sum forces in the Y to say N is equal to what? N is equal to 500 pounds. Has to be. So then friction max is equal to 500 pounds times 0.5, which equals 250 pounds. So that's this, right? So then impending motion would mean, hey, P, these two have to be equal and opposite. So P equals 250 pounds. Comes out the same, right? It works the same. Oh, sorry, you couldn't see that end part. All right, so remember, that this is still static. It's the top of the graph. So it comes up, straight line, drops down like that. That's the graph, right? So that's right here. This is called impending motion. For motion to occur, P would have to be greater than 250. That's typically how we write it. So we can determine how much load would be required to move this thing, right? We can determine that. It would be P greater than 250 pounds. All right, I hope that helps with the resultant friction force and this thing called the static angle. It goes here between N and R. That's important. So if FM flips over, right? It's FM, and like if, well, hey, I want to push on it, right? Then it would flip over, then R goes in here, and then the static angle always goes here. So just keep in mind, it's static angle is always from R to N, and R is always between the two components. All right, hopefully that helps with your next assignment. Have a great weekend. And those of you that came and helped me this morning, I do appreciate it.